live. How's it going, everyone? Hope you had a good week off last week. Today we are back in action, and we are continuing with skflow and CIFAR10, but I did a little bit of research, as usual, 5 minutes after the video last time, on what my issues were reading the data, so now I actually have the data set in question, CIFAR10. I just downloaded directly, not trying to get it via TensorFlow or anything. And you can read it in with Numpy, do whatever, and you can look at the pictures, which is always nice. So that's what we're going to do. And I did a quick test of how it read in just using a simple logistic regression. Got 25% accuracy on 10 classes, which is better than random guessing. So there's that. But let's see how good we can do here. Our goal is going to be to replicate the official TensorFlow tutorial on doing CIFAR10. Of course, their tutorial just has you running their sort of pre-trained code, which is a little unfortunate, but we'll be poking at that code and, seeing if we can build the same model or something approximating it. I may or may not also do the same sort of data fiddling that they do. They flip all their images around, they distort the brightness and all this other stuff. We'll see if we do that. Right now I just want to focus on getting something going. So let's get started. That's cute. Naturally, things don't work. Hang on. I think that's tragically died. This is what I get for not testing things, although I'm pretty sure I tested it. There we go, okay. Little Slimeox troubles there, but we're back. Defining some stuff. We're importing skflow, we're importing sklearn, some TensorFlow models, all this jazz. And I've downloaded the data already, so I'm going to go ahead and load that. And so the labels are just the first column of the data here. Let me show you A of 0. A of 0 being the first data point, right? Yeah. So you just get a bunch of rows here. What is A dot shape? Yeah. 10,000 rows of 3,073 things, which is, of course, 32 times 32 times 3 plus 1. Boom. Because it's a 32 by 32 image, there are 3 color channels, red, green, and blue, and there's one more column for the actual label. Which category of thing is it? So we've got that, we've read it in, we have created our labels, all things 1 to 10. Let's just verify that. Yep. And we've created our images. Let's take a look at images 0. What is this thing? You might look at that and say, well, that's interesting, but how do I actually, see that? Well, let's use plot.imageShow, and now you can actually see it. And so you see a very grainy picture of some kind of car. Maybe it's a truck. I'm gonna be honest, I cannot tell which way this car is facing. I think maybe left. It could still be facing to the right, and it's like a pickup truck. So there's some challenges, even for a human, to understand this. Let's have a look-see at image 1. This is clearly a frog, right? Alright, so we understand some things. We're going to unroll these images because images 0.shape, you'll notice, is the 32 by 32 by 3 color channels. We are, however, going to need, for our simple model, we're going to need a version that's just the 372 independent features, where I say independent in quotation marks, of course. Because pixels that are next to each other, not actually independent. They're quite correlated. Let's get this dense to one hot business going on. Let's start our TensorFlow interactive session. We got 4 threads, still going CPU hardcore. Fantastic. Okay, and we're just going to use, first off, TensorFlow linear classifier. So you might recall TensorFlow linear classifier. This just implements logistic regression, essentially. Does it even talk about this? It doesn't specifically. I'm 99% sure it just implements logistic regression. So I've just made up some things here. I've got 10,000 samples, right? 10,000 samples, 10,000 pictures. So I said batch size of 100 and do the 1,000 step thing and this learning rate and just see what you get. Let me crank that learning rate up, actually. Oop, there we go. And then you can just run fit. It goes a little bit. It's pretty quick because it's linear regression, so, or excuse me, logistic regression. So there's not that many parameters to fit. There's going to be 10 times 3,072. So that's not bad. Figure 30,000 parameters. Boom, look at that. Let's see how good we did. Yeah, 26% accuracy here. Let's crank the number of steps up. That was pretty quick. Let's do twice as many, shall we? So it's going to take a little bit longer, but it's going pretty well. Did I? I did. Yeah. So this loss, randomly, we're doing a little bit better. Started at 1175, started at 1097 here. So not too bad. It's cranking, it's going along, it's moving, it's moving. It's not going to be much better. It's got a new score, and it went down. Okay, so we overtrained maybe. That's interesting. And here I'm just computing the accuracy on the training data itself. If I can't even do a good job at that, I'm probably not going to make a lot of progress on anything else. There we go. And you can see the loss going down, so that's good. And again, we're back to that 26% accuracy. All right, let's have a look-see at what these feature vectors actually look like. Remembering that they are, in reality, these 32 by 32 by 3 things. So classifier.weights underscore, if you have a pure skflow model, that's how you can get all the weights. So I got W here. And W is, of course, 3072 by 10, because there's 10 classes. You're computing a score for each possible output based on the input features, of course. So I want to show sort of these 10 classes at a time. What am I plotting for each one? I'm saying, oh boy. Interesting, interesting. So I could just instead, right, because I haven't unrolled the features, or because I unrolled the features, reconstructing them back into the proper images. Not the most obvious thing. But if I just said plot.pcolor W, for example, I could look at all the features at once, which is not particularly illuminating because that's 3,072 in a row. So let's not do that. That's not going to do the right thing, is it? Because I've got 32 times 30. Oh, this will be the first, the reds, I think. Question is, how does unroll work? Right? So how did I unroll here? Images unroll. Oh, images unroll. I just rebuilt it from the original. I didn't do the fancy reshaping business. If I look at images 0, for example, this must be the red channel, the blue channel, the green channel. This is getting a little confusing at every position. Images 0, oh, that's a particular channel. No, that's images 0, 0. That's like the red channel. What's going on here? 32, oh, I transpose. Forgot that. So I put it in reshape it this way because that's the order that the actual features come in, and then I transpose it. So I'm just shifting around the ordering of the dimensions, which in this case does mean actually moving certain criteria to different positions. So if you said images of 0, everything, red channel, you get a 32 by 32 thing. So for example, plot that image show of this. This is just the reds. So how red are the things in this category? Just the blues. How blue are things? And just the greens. I think this is working right. I might be lying. That's interesting. Although, really, blue is strong here. I see. This is strong because it's kind of gray, and so it has lots of colors in general. All right, that was an amusing diversion. However, what the real situation here is that our W weights is gonna have. Let me see this here. It's gonna have W of 0 gives me 10 values. I see. Right. It's 1024, of course. So that should be just the reds, if I think about this right. Yeah, I think that's right. So what I really want, think about this right. I just want an array of 10 by 3 things. I want 10 things going across and 3 going down. I believe that's right. And so now, which column am I in is just, I guess that's XX. Yeah. And this is 1024 times YY. This is 1024 times YY plus 1. And this, there we go. That should be vaguely what we want. Let's see if that works. See if I blow up in my face. An object is not callable. Figures. Oh, right. Also, I got that a little goofed up. So yes, an integer is not a function, and I wanted 3 by 10. So this should be XX, XX, YY. Let's try that. See if it's nice wide thing here. There we go. So now you can start to see some of the overall features in each class of things. So this is cars, this is frogs or something. Let's quickly look that up, what the various feature classes are. Okay, those are not the, oh, those might be the classes, yeah. Airplanes, cars, birds, cats, deer, dog, frog, horse, ship, truck. And you can actually see some overall features, which is kind of interesting. I would not necessarily have expected to see even that. I want to do one more thing. I want to like plot the reds red and the green's green, the blue's kind of blue. Does this have... Oh boy, oh boy, oh boy. Pink is an option. Okay. Not gray. Red? Rainbow. Nope. Green? No, there's gray, but not green. And blues, of course. Bone. Cute. Winter, spring, summer. I'm not even sure what that's getting at. Let me see. Color maps equals plot.cm dot matplotlib color maps. What are those? There we go. Color maps reference. Choosing color maps. Viridis, Inferno, Plasma, Magma. Sequential color maps. Blues. Blue, green. How do I get the blues? Alright. Here we go. Sequential. CMap, sequential, blue. Where is it? Plot.cmap of name. And CMap list is... Oh my gosh. It's sequential blues. Reds, greens. CMap category, CMap list and list, CMap list. Buddy. Oh, CMap category, comma, CMap list. And you're saying plot.get CMap? Is that a thing I can do? Huh, what do you know? I did not know you could do this. Blues, does that work? Hey, what do you know? Reds. And let's just copy that. There we go. And this one is red, green, blues, and this one's going to be greens. Color maps. Those are all good color maps. Superb. So CMap is now going to equal color maps of YY, XX. Right? Losing my, yeah, XX is which color I'm on. Let's see what that looks like. Big money, no whammies, excellent. This is just to see what's more green or what's more red. Although, I have to wonder, is it this or is it the reverse? That's really what I need to know, right? Okay. All right. W of rights. That's W of 0. That's the first class. Those aren't particularly interesting. What's XX? All right, I have an idea. We're going to grab this guy and just look at him. Oh, come on. Dot reshape. 32, 32. Let's look at that, shall we? Ugh, let's print the whole thing. Of course I can't print the whole thing. List the whole thing? If I list it, it should show me everything. There we go. That doesn't help. So where, this is the final guy. So the question is it higher or lower as you get to the middle on the left? So let's just look at all the rows and the first column. This is no longer a list. There we go. Just plot that. Oh my, that did not work. That did not work at all. Plot that show. Kill that. So it's lighter colored over there. Try that. So it's lower. So lighter is lower. So that makes sense. As opposed to lighter being higher. So the more the color it is, the higher the value is. So again, we're going to look at this. We're big on sweet visualizations here. Click the button, okay. And so you can sort of see some general shapes here. And it's not, yeah, and here, your whatever this class is, class 7? Let's see, what's class 7? The horse? Interesting. Lots of red here. Or sorry, lots of red here. Same place, you want less green. You want a little bit of blue. That's kind of interesting, and not so much blue up here. That is odd. I kind of would have expected the opposite. Although maybe it looks like horses rarely have blue in the background. Maybe you got brown in the bottom? Maybe something like that. Ship? Does ship have a lot of blue around? I would have expected more blue. Well, this is just logistic regression anyway. We haven't done anything fancy. And good. I haven't wasted too much time goofing around with logistic regression. All right, so now we've got sort of a basic setup. We can run some stuff. That's good. We're using skflow. We're doing some CIFAR10. We're modeling some images. Well, what we really want to do is build a better model. And to that end, we're going to build a convolutional model, convolutional neural network, just like we did for MNIST. But this time, it's going to be on CIFAR10. And I've actually stolen some code from what I wrote for MNIST, which is really stolen from the skflow tutorial. And we now know how to extract the weights from that because I did a pull request and figured that out 3 weeks ago or whatever. And now that's part of skflow, and you can figure out how to get those stupid weights. I'm hoping that there will be an easier way to do that in the future. Let's just pull up our generic pooling layer. Okay, and I believe this is generally the same. This needs work. Yeah, no duh. All right. Righto. Let's copy some of this information. There we go. So we're doing the same thing. 10 classes, whatever. Yeah, there are still 10 classes. What do you know? However, we are no longer modeling digits. Yeah, let me do that. Okay, that's better. So X is going to be images on roll. Y is going to be labels here, right? Yeah. Let me say X equals, oh, X is not going to be images. Unroll, X is just going to be images. Got to be careful about that now. Because I have 3 color channels. That matters. So let's see if we can build this up the right way here. Let me just X equal images and Y equals labels. Let's see how we go. Let me start building up the machinery here. Yeah, that's fine. I'm not going to worry too much about this scope business at the moment. Oh gosh, that is way too many print statements and it is going to freak out. Yeah, hang on. For attribute T, not in list of allowed values. Right. So let me do this one step at a time here. We got x. X is reasonable. X dot eval. X dot eval. Yeah. Okay. And y is the thing. Y is just array. Nothing fancy about y. Can I do that? I cannot do that. Why not? For attribute t, not in list of allowed values. Oh! Because images is, of course, of data type uint8. Because probably I was trying to save memory. But it's not too bad. So if I use 4 times as much memory for uint32, for float 32, that's going to be okay. So in fact, let me go ahead and do that. numpy.array of images dtype equals numpy.float 32. Let's see if I crash my machine when I do this. If the stream suddenly cuts out, you'll know that's what happened. Watch my memory not change at all. Interesting. Alright, well that's good. Images. Fantastic. And x equals images, and y. It's probably going to complain about y as well. We'll find out. We'll get to that. We'll burn that bridge when we get there. It's as usual. Numpy data has no objective shape. Right. Do the TensorFlow stuff. Oversharing. Variable convolution filters already exist disallowed. Did you mean to set reuse? I didn't. Let me just kill that. Easy solution. Just kill everything. Kill it with fire. Alright. Rerun all that, that's fine. Redo our dense to 1 hot stuff. Get our labels hot going on. Also, we need labels hot these days, don't we? No, we don't. We don't need labels hot. That's true. I don't need images at all. I do need my TensorFlow session. Do that. X equals images. Label. Y equals labels. Of course. Life's good. Onward and forward. Alright, that actually worked. What happens when I do that? Dimension 10, dimension 32, 32, 32. Oh, because there's 32 output filters, right. It just happens to be the way it is. Max pool 2x2 is not defined. Let's define it, shall we? There, now it's defined. Did that. What does that look like? 16 by 16 by 32. That's good. That's about what we expect. Alright, the next convolutional layer, oversharing. Variable convolution filters already exist. Really? That's not what I expected to see here. Maybe because it's my scope is all jacked. What happens when I do that? Oh, that's fine. Alright. Usual, I run out of water way too early. Hpool 2 flat then. So this needs to be of the appropriate dimensions, which is going to be 8 by 8 by 64. That's our final, our flattening that layer needs to be 8 by 8. And I can tell that because this pool, the final pooling layer is 8 by 8 by 64. So that's convenient. I don't recall what the actual sizes in the CIFAR are. Right now, I just want to get something working. This is in the same scope, actually. So let's do that. It did not yell at me. Excellent. Actually, now that I think this is probably going to work, what happens there? Yeah, what happens when I do this? Return outside function. Well, there's that. I say S? Is that something? Has no attribute get shape. Yeah, figures. Y dot get shape. Why is Y? Oh, because it didn't TensorFlowify it. TensorFlowify. That's a verb now. I'm just gonna run this whole model, that whole function, now that I think that's actually working correctly. Let's be bold. We specified our classifier. We specified our convolutional model. Got our batch size, number of steps we're taking. Good gravy, that's a lot of steps. Let's see how this does. Oh, shoot. I need to take out these print statements. Danger of running a code. There we go. Much better. Remake our classifier. Now we're going to fit. Let's see what happens. And we'll keep an eye over here. That was step 1. It's supposed to be every 100. We get a new information on the step. That's taking a long time. Oh, come on. Come on. You can do it. You can do it. Not even that many models. Oh no. This is with 64 parameters in our final hidden layer densely connected. Granted, that's coming from 8 times 8 times 64 neurons before. So that's 64 squared, which is 12, which is like 4,096 things in that layer. So, you know, that's a lot. Yeah, that's a lot of things. So we're gonna see if this goes anywhere. While we're waiting on that, let's look at the actual CIFAR10 model. We don't need this color map stuff anymore. I want to know, how do they specify their network? Because I know back here, they give you sort of a bird's eye view of it. They say, oh yeah, we got these 2 convolutional layers, and then these two densely connected layers, and then the softmax, the logistic regression. And here's just another picture of the same thing. What's this norm? Local response normalization. What is this? The 4D input tensor is treated as 3D array of 1D vectors along the last dimension. Each vector is normalized independently. Within a given vector, each component is divided by the weighted squared sum of the inputs. Okay, so yes, you normalize each vector along the last dimension. So you've got a 3-dimensional thing, and in each spot you've got some line of things. Maybe we should be doing that. So max pool 1 or 2 or whatever here. That's gonna have, what's it gonna have? Max pool 2 or 1 or whatever. Max pool. In this case, it's 16 by 16 by 32. None being the batch size, of course. So it's going to be along this last dimension, this 32 like channels of information. It's colors when you first throw them in, but of course it's just channels at this stage. Arbitrary divisions in a way. Different features we're pulling out is what I should really say. Different structural features we're pulling out of the image. Ugh. So it's saying that each, look at this again, we normalize each feature within itself. So that's an interesting idea. I'll worry about that when I have anything running at all. That will be the time for me to worry about that. Alright, that's taking a long time. I don't want to wait that long anymore. Nope. How bad are we doing? Classifier dot. Note that there's no weights because we used a custom model. Images unroll is not what we're using anymore. We're using images. Straight up. That takes a while just to score. Ugh. So this is what I get for not having a GPU that works with TensorFlow. Maybe I will fight with that some more at some point, but probably not. All right, there we go. It worked. Accuracy. 0.1, so that's basically random. Because if you randomly pick one of the classes, you will get an accuracy of 0.1. That's right. Let's see. So let's... Sorry about that. I want to be able to do more with this, so let me compute fewer things. That should be the easy thing to do here. So we're cutting the number of filters here to 16 into 32, and so this will be 32 here. I'm going to stick with 64 output filters. That sounds reasonable to me. So we're making a little simpler model, just to see if we can actually train it. Let's do that. So that's step number 1. So initial loss is that. I wanted to know every 100 steps or whatever how it does. That is still taking some time, however. The most boring part of machine learning, waiting for your results to come back. If you're working normally, you can just work on a different model at the same time or launch a bunch of models at the same time to go. When you're working live like this, I don't have that luxury. I'm using all of my machine right now. These CPUs, they're working pretty hard, you know? I appreciate how hard they're working. And they got to compete with some video streaming software at the same time. So they're not doing too bad. I appreciate that. Using half my memory, not bad at all. That's taking forever. Oh my gosh. Classifier dot steps? No, okay. Let's just try to score that. I'm going to say steps 20 just to be silly here. Oh yeah, slightly better there. How fast can I do 20 steps? Alright. Time it. I don't want 20 steps, I want 200 steps. So this I'm guessing is going to take on the order of 30 seconds. I don't want to time this. I don't want to time it, actually. I just want to time. Time it will run something multiple times, given the chance. If it doesn't take a long time. But by just running time, I can get some more reasonable information. Okay. Now I can tell that it's going somewhere. That's much better. But it's kind of getting stuck. Oh, the loss got worse after that set. And it seems to be kind of bouncing around here. Alright, but that did something, surely. That spent 20 seconds. Oh, and my Python crashed. Part of the risk of the business, you're having your Python crash on you. That's just what you got to do, though. Alright, let's reload stuff. If I were really serious about this, of course, I would save off my output anytime I needed it. But we're just showing things off here, so that's not a big worry. Don't want to fiddle with this model at all while I'm here. I think I'm actually happy with it. Yeah, this model's okay. And let's try running again. Running my TensorFlow, doing all that jazz. Did I not run? I didn't actually do a TensorFlow session, but I guess it initiates one when you run the classifier.fit. That's nice. Didn't realize that would be that. bad. Not receiving video data at fast enough rate. No, my stream's not happy. That's okay. So 22 seconds to fit, a few seconds to score. Really bad accuracy. That's okay. That's totally fine. Nothing wrong with that. Here, however, I'm going to grab my information on these other layers. So we can actually look at, and by actually look at, I mean I missed some parentheses in all of these lines. In the pull request I had it fixed, but for just this I didn't, of course. Okay. We can just look at all the weights here. And you can say, oh, there's a lot of weights. But the point is, you can actually get your hands on them. If I say, for example, wconv1 equals whatever this junk is, now I have the first convolutional weights. First layer convolutional weights. Which is, of course, these little 5x5 patches times 3 color channels times 16 outputs. So if I plot a little 3x16 subplot with a little 5x5 in each area, I could see something interesting, I think. Let's do that. And since this one actually has colors, we'll do some real colors here. So 3x16 thing. We are now using WC1. We got all the rows, all the columns, XX, just what channel we're on. Let's see if this actually works. So we're going to plot the weights for all the features we're extracting initially. Size new array must be, oh right, it's not a 32 by 32 array anymore. It's a 5x5 array. Right, and now we're actually going to take a look at this. There we go. Coming online, perfect. And this may or may not be illuminating. That's kind of like that. You can see the reds, the greens, and the blues here. Right. Of course this isn't illuminating because the model is garbage. So we shouldn't expect this to be particularly interesting. But it's just that's just curious. Did I fiddle with my... Hang on. Plot style. I want to update my style. No reason to use this awful style. Matplotlib style. I just have to forget the exact incantation. Customizing plots with style sheets. That's not really what I want. Plot.style.use ggplot. Much better. So ggplot, much prettier plotting style in general, in my opinion, a little softer on the eyes. In this case, not a big deal. And again, this is all just random garbage because the model is still random garbage. Funny how that works. Funny how that works. And we could play a similar game on this second convolutional layer. Let's actually do that. Let's have a little fun here. This is convolutional layer 2. So conv layer 2 filters. Color maps no longer matters since we no longer have that sort of obvious feature set. 16,32. And I think it is still a 5x5 image. Filter shape 5x5, 5x5, yeah. And CMap, we're gonna make all these just gonna be gray. Just for my own sanity. Plot.cm.gray. let's do that. So again, second convolutional layer. You just look at the weights. So these will take inputs of the previous layer in kind of an interesting fashion. And we expect these to be random garbage. Note here that I've got 32 times 12 additional things to plot, so it's going to take a little longer. Yeah, you know, 5 times as many things. It's not a very fast library to begin with. Doing the subplots is a lot of effort. See if it ever actually gets through here. There it goes. Okay. Okie dokie. No, any day now. Any day now. Oh, it's still thinking about the for loop here. Index 16 is out of bounds. Oh, well, I'm still calling WC1. Well, that was my own stupid fault. That was my own stupid fault there. Oh boy. May crash something. Alright, I think I crashed IPython, unfortunately. Oh, wait. Hang on. No, we crashed IPython for sure. For sure. Oh, no, hang on. We're back. We're good. We are so good. Don't need to fiddle with that. Right, the problem is trying to plot WC1 in a place where it wanted WC2. Try this one more time. Really should get a better plotting library here. So P color is too slow. Let's do a quick lookup on that. Plotlib P color slow. What's the faster thing to do? This guy says, hey, P color is slow. What are all the alternatives? Image show. Image show is just an image. Interesting. You may not need to worry about it depending on how you use P color. One wants to set interpolation equals nearest to an image show. Interesting. Oh no, it actually worked. Also P color mesh and P color fast. What's P color fast? See this page for a nice comparison between them. So this is just a diversion of data visualization, because that's half the problem when you're doing this kind of stuff. Image show follows convention used in image processing. The origin is in the top left corner. P color mesh. Let's try that. P color mesh. Plot.p color mesh. Does this work the same way? Yeah, I think it does. C, X, Y, C. Let's give that a shot. Let's see if that saves us some trouble. Alright, if that doesn't go anywhere, then we're not gonna worry about it too much here. We'll move on to other things like adding more layers to our network. Alright, that's taking a long time. I don't want to do that anymore. Instead, I want to crash my Python application. I have to threaten to do that and kill that. Right. There we go. So we're not worried about that. We wanted to look at CIFAR10. What do they actually do? Does this actually specify their model in TensorFlow proper? I don't think it does. That just trains the model for some sense of train. Calls the function that trains it. Builds a CIFAR10 model. That's what I wanted. Silly me, silly me. Variable on CPU, variable with weight decay, distorted inputs. I mean, that's interesting. I just want to see what the model. Here's the model. So they do variable. They're doing some interesting things here. But they're doing 5 by 5 with 3 color channels and outputting 64 weights. They're doing a 2D convolution, yada yada. Pooling. I think it's typical 2x2 pooling, if I understand that correctly. Some interesting normalization here. And I guess there's nothing stopping us from adding these things to our model either. I'm going to choose not to implement this normalization right now. I'd rather get all the layers in there. So 2 convolutional layers, both 5x5, both outputting 64 feature layers, or features. And then, what do they got here? 384. So that's 256 plus 128 neurons on that layer. And then 192 on the next layer. So 128 plus 64. So let's do something similar, but not as ambitious. There's one hidden layer, there's another hidden layer. Wait, deep neural net. I can add multiple layers, can't I? skflow.ops.dnn creates a fully connected deep neural network subgraph. Hidden units, list of counts of hidden units in each layer. So for us, let's say 96, 48, which is to say 64 plus 32 and 32 plus 16. So of similar style, but not the same thing. Not the same thing. How did they get their final? I'm curious how they went from their final pool layer to this layer. Where do they flatten? Pool.getShape as list. I see. So that's how they do it. You could just do this with a reduction operation. It's kind of a strange way to write a for loop to do that, but that's okay. So yeah, they reshape it that way, whereas I've manually sort of computed that here. Either way's fine. Their way's probably better. I just happen to do it this way. So we've got considerably more features going on. You know what? I'm going to cut down the number of features. Let's say I only want 16 coming out of this. So 16 and 16. Save me a little bit of processing. Let's do that. Let's see how bad this is. Oh, okay. That's not the end of the world. It's probably going to take a similar amount of time to run, which is interesting. Of course, now when we grab our densely connected lates, that's going to be interesting. So what is that? Now I've got 2 densely connected layers. So I don't want to print anymore. That's .shape. What is that? That's 1024, which is of course that's 8 times 8 times 16, or 2 to the 3 times 2 to the 3 times 2 to the 4, 2 to the 10, 1024. I bet if I say layer 1 next, bam, we get the next layer. Life is good. Life is good. Densely connected layer 0 weights, where 1 weights. Of course, we haven't pulled the biases out of here. That's all right. All right, let's take a look. Terrifyingly, let's take a look at the accuracy, which I'm sure is pretty bad still, but that's okay. Oh yes, it's still quite terrible. Let's let it run a little bit longer, shall we? And then we'll end the video and see how good that we did. But we've replicated the core of the model. At least I've shown how to use skflow to build this kind of model, this convolutional neural net, adding arbitrary things from pure TensorFlow for something like CIFAR10 instead of just MNIST. So at least you have another example to work off of now. Often that's half the battle. See one example, you can get a lot of what's going on. If you see another example, you can learn more even. because you see, oh, this is different from that. All right, that's going. 200 steps, something happened. Loss goes down, you know, that's a plus. Accuracy, still pretty bad. And I think it is uniformly distributed across the 10 categories. So there's an equal number of cars and airplanes and dogs and frogs and deer. I think it's deer. I don't actually recall. Is it deer exactly? Yeah, deer is a category. Nice. Loss still going down, making progress. We are almost halfway through. I'm gonna let this crank a little bit. We'll see if next week, if I want to spend more time on this model to like actually get a good model. I mean, at this point, part of the problem is just it takes a little bit of time. This model is just a little more complicated than the MNIST model. Partially because these images are a little bit bigger. You'll notice that Google cut theirs from 32 by 32 to 28 by 28. We could have done the same thing. Or to 24 by 24, excuse me. And there's 3 color channels, so there's sort of 3 times as much data already, plus a little bit around the rims, and this model is a little more complicated. It's got these 2 densely connected layers, followed by the end. So there's a lot more parameters that need training. And also, obviously, there's a car can be a very general thing, whereas a 0 is a little more straightforward in what a 0 is. So I'm not surprised at all that the error rates are considerably worse. But again, that's okay. The purpose of this video is not to build highly accurate machine learning models. It's to learn how to build machine learning models. Getting it accurate, well, that takes a lot of time. You turn this knob, you twiddle with that. You look at your error rates on your training set and your testing set and your cross-validation set, and you say, I wonder, is this working? Does this mean I need more features? Does this mean I need this, that, or the other thing? But for large models, that's difficult to do interactively, and that's why I tend not to do that. Here we're just focusing on, can we get this stupid software to work? Because that's often half the battle. Alright, this thing is almost done here, and I have a feeling it's not going to be super awesome. Although we ran it significantly longer. That'll be done here in just a second, so that took 3 minutes. Oh, shoot! I tried to fit it again. Whew. Hopefully it's still okay. Let's compute the score. And not much better. Yeah, I suspect the normalization will be important if you want to make this better. Getting more data that twiddles the data you have, flipping the images, looking only at the center, messing with the contrast, stuff like that. That'll be very important. But at least you can build a model like this, and you can visualize your weights now. So that's a very useful thing to do. Your reds, your greens, and your blues. I like this image. This is nice. With the GG plot, it's much softer. If this is a country flag, someone please tell me. The red, green, blue, or blue, green, red, either way. That'd be an awesome country flag. And so, well, there we have it. That's CIFAR10 done in skflow for some version, an analogous version of the Google model. So I hope you guys enjoyed that. That actually worked reasonably well. And next week, we'll see what we get into. If you have a particular topic you would like me to look at, or a particular piece of software you'd like me to try to install and use, hit me up on Twitter, I'm on Reddit, send me email, leave a comment here. All those things are great. All right, you guys have a good night. Keep learning.